Hi, everyone. Hi, welcome. Nice to see so many of you here. This is terrific. I'm Alyssa Goodman. I'm a professor from the Astronomy department. And importantly, I teach a course here, a general education course on prediction. And while Kelsey and I are both astrophysicists, it is not that reason that I have invited her here to talk first to my class this afternoon, which she kindly already did. So she's already been working for 3 hours for us, but also to you tonight. It's actually because of my interest in prediction and her interest in essentially questions about the future and even about the present that we may not be able to answer, but that we can think about in creative ways. And I had heard from Kelsey that she wrote this fabulous book called Into the Unknown. And she very quietly encouraged me to read it. She's like, oh yeah, you could read it if you want. And I loved it. And I just completely loved it. And I loved the idea that she, as a serious card-carrying physicist, I'll get into her credentials in a minute, was willing to take her interest in philosophy and things beyond the normal things that people think about in physics and mix it into first a course, and she'll explain how her course became this book, and then this book. And it's surprising. That's what I can tell you about the book, okay? In other words, you think you're going to read some book about science and about physics and about how we know what we know about the universe, but it's really about who we are as humans and how we think about what we know and what we might not know, and should we think about certain things in certain ways? And I don't want to steal her thunder, and we're going to have a conversation afterwards with Avi Loeb and Peter Galison, who are here. So I don't want to take too much time. I'll just give you a little bit of an introduction to each person. And before I do that, let me just also thank the Harvard Bookstore and the Gen Ed office for helping us arrange this, and also Melissa Franklin, who's over there, who runs this series of science lectures with the Harvard Bookstore. So thank you, everybody. And so Kelsey, in her official introduction, is a professor of astronomy at the University of Virginia. She's also had many leadership roles at the university there, like being Associate Dean for Undergraduate Education. She's also been recently the president of the American Astronomical Society, the president of the Astronomical Society of the Pacific. Many, many honors and awards that if I were giving you an introduction to an astronomy lecture, I would read all of them for you. But what's most important is her interdisciplinary work on things like studying awe and giving a TED Talk about her outreach program involving children in rural areas being able to have access to dark sky. And I highly recommend that talk. And she writes for the New York Times and Scientific American and all these things. But the style in which the book is written is very conversational. And I think you'll hear Kelsey talk like that tonight. And then let me just move on before I take too much time here, and say that we have, again, as I mentioned, two of my colleagues here, Peter Galison from the History of Science, and he's a university professor, so he's from the university, and Avi Loeb, who's a professor of science. And so Peter and Avi are both involved in something called the Black Hole Initiative, which Avi is the founding director, and Peter is the current director of the Black Hole Initiative. So some of our conversations afterward will be about black holes, I'm sure. And Peter has an interesting background where he's an expert both in history and the history of science and also philosophy and also physics. And so he's kind of a perfect person to discuss this book. And Avi also has deep interests in many areas of astrophysics, but also, again, in philosophy and humanity and how we know what we know. And one of the things that he did was found something called the Galileo Project, which you will hear about in a little while. And they both have incredible credentials in their own fields, which I will not enumerate for you, so that I can instead welcome Kelsey. And the plan for tonight is that Kelsey's going to give us an introduction to her book for about 15 or 20 minutes. Then the three of us will have a discussion for another 20, 25 minutes, and then we'll ask you for questions after that for, say, another 15 or 20 minutes. So that is the overall plan, and I will turn over the mic to Kelsey, and thank you very much for coming.
Hi. Hi. Thank you for being the kind of people who come out on an evening to think about big existential questions and nerd out with me on them, which is one of my favorite things to do. So I'm Really excited to be here. I want to start by laying a little bit of groundwork for why I wrote the book. I think, many of you, I think in the room have probably written your own books. I'm sitting at Harvard. But I think you will get that writing a book takes some effort and you have to have a real motivation to do it, right? You're not just going to get out of bed one day and finish it. And so I wanted to share with you, a little bit of my motivation behind why I embarked on this project. Now, what I want to say is that my perception, and I don't have any data to back this up, but my perception is that amid modern life, we are becoming increasingly disconnected from the natural world in general, and absolutely disconnected from the universe in particular. And I think this is quite problematic. And this disconnection separates us from some of the big, beautiful ontological questions that have really sat at the core of what it means to be human for all of human history. And so with this book, my hope is really to invite us all into a space of existential curiosity that we might not always give ourselves permission to be in. And so I really want to invite you all to give yourself permission to think about some of these, ontological and existential questions that may in normal life seem trite and almost make funnable of. But I think that they matter, and I think that it matters that we think about them. So what I thought I would do is start by reading a brief excerpt from the introduction of my book, and then tell you a little bit more. So I'm going to have to literally read my screen because try as hard as I might, I have not memorized my own book. Okay. You may go about your normal life and feel like things just work. The microwave heats your frozen meal, if not uniformly. Cars drive and are even starting to drive themselves. Computers calculate all kinds of things, some of which are even useful. We've sent spacecraft all over the solar system, and we are on the verge of sending actual living people on similar escapades. To be sure, we humans have learned a lot, and we seem to have more or less understood the world of our everyday lives. So you can be forgiven if you think we already pretty much know everything. But I'm writing this book and giving this lecture with the hope of dislodging that comfy notion from your brain. Considering how limited and provincial our experiences are, I find it astounding that we've even figured out as much as we have about the universe. One of the reasons our world seems to make sense is simply that we are used to it. It is easy to go about normal daily life and take basic things for granted. They just are. For example, right now, you may be sitting on a chair or standing on the floor, which is true for everyone in this room, or sitting on the floor, but hopefully not standing on a chair, which is not true of anyone in this room. And that's just about the most everyday kind of experience you might have. Take a generous moment and think about gravity holding you down, literally pulling your mass toward the mass of the Earth. Why does gravity do that? Just because it does is not a very satisfying answer. And if you've had the pleasure of interacting with kids, they might let you know just how unsatisfying just because is as far as answers go. While we're on the topic, what even is mass? To be fair, we do know a bit about what is under the hood as far as mass and gravity go. But just because I know there is an engine under the hood of a car, that does not mean I know how it works, which is factually true in my case. Coming to terms with our unfathomable insignificance in the cosmos may be impossible. The scale of the universe and space and time extends so far beyond our ability to comprehend that sometimes I feel the best we can do is try to comprehend that we don't comprehend. Even for astronomers who think about these concepts daily, the full scales of time and space are largely abstractions that many of us have become desensitized to, perhaps out of necessity, to keep our sanity. Staring into the abyss every single day can take a toll if one doesn't get a touch habituated to it. Yet here we are on this tiny little speck of a planet, trying to understand not just this tiny speck we call home, but the whole universe. So here are some of these big questions that keep me ruminating late at night, and I have given myself permission to ruminate on them. What happens inside black holes? What are dark matter and dark energy? My favorite, where did the universe come from? What is the nature of time? What determines the laws of nature? Is there extraterrestrial life? And are there hidden dimensions? I hope that some of you have at least thought about some of these. Now, we don't have answers to these questions for different reasons. Sometimes, I would argue, we just need more time. For example, we have only had the two pillars of modern physics, general relativity and quantum mechanics, for like a century, right? Like that's like a hot second in the scale of the universe. So we might still make more progress with time to do more experiments or create new technology or develop new theories. And so we have to be honest about how much time we've had as humans to do this work. The second limitation might actually be cognitive. We have to admit that our brains have limits in terms of their abilities and logic. Now, we like to think of ourselves as highly intelligent, and certainly on the Earth, we seem to be the apex of intelligence, and I'm not here to argue that, but I do think it is worth keeping in mind, and I'm sure some of you know this, that human DNA is only about 1.2% different than that of chimpanzees. And yet I am sure, and I would love to, this is one of those things I would love to be proven wrong, but I'm pretty sure that there is no way I'm going to teach a chimpanzee calculus or thermodynamics or general relativity or quantum mechanics. And so for me, that begs the question, as I think about our own cognitive limits, what might we be capable of if our intelligence were yet another 1.2% further advanced? Now, to be clear, I want to be crystal clear on this. I am not, absolutely not, advocating for transhumanism. What I am advocating for is some intellectual humility and an acknowledgement that we may not be capable of understanding everything in the universe. And then finally, another reason we may not understand, and we may not ever understand some of the answers to these big, beautiful existential questions might just be truly fundamental. Right? We are embedded in this universe we are trying to understand, and we are subject to its laws. We don't, at least not yet, have the ability to get out of the fabric of space-time to observe it. No matter how advanced we might become cognitively or technically, we may never be able to probe or interact with some aspects of the universe. Science can take us right up to the boundaries of where these existential questions are, but then where are we left? And that's where this book really comes in for me. So I want to leave you with one more excerpt from our book, and then we'll move into the panel. So this is an excerpt from slightly later in the introduction. Because of the unknown and potentially unknowable nature of the topics in this book, we will often find ourselves at the convergence of empirical inquiry, also known as science, philosophy, and theology. This can be an uncomfortable space to be in, but this is also where some of the most interesting questions dwell. So let's not shy away and avoid talking about complex and loaded topics just because they are complex and loaded. The fact that they are complicated and have significance in myriad belief systems means they really deserve to be talked about, but with a hefty dose of care and respect. One final request before we get going in this book, or in this lecture: be curious. You did, after all, choose to pick up this book or attend this lecture, so you must be at least a little curious. Remember all of those why questions you used to pepper adults with when you were a child. Now is a great time to rekindle that mentality and pretend that no one ever told you because I said so, which is just about the most curiosity-squelching response an adult can give. The world is a lot more interesting if you are curious. Being curious is also how we make progress in science. And please tolerate "we don't know" as an answer. And by we, I mean like all of humanity. When you get these "we don't know" answers, part of the challenge is to ask, how could we find out? If you crack that puzzle, you may have a Nobel Prize waiting for you down the road. All right, with that, I would love to invite all of us here, or hand it over to Alyssa, or whatever it is I'm supposed to do.
Questions back up. Do you guys want to say anything to get started, or should I just ask you questions? By the way, while Kelsey is getting comfortable, I need to point out that this beautiful watercolor that you can come look at later is a gift that Kelsey gave me, because among other things, she's a very talented painter. And that is a picture of turtles all the way down, which you will see comes into play as we have our discussion here. So again, I've mentioned that Avi and Peter are two very unusual people at the university because they have interests in many fields beyond the one that they were originally trained in. And in particular, I think they're two of the people who understand what it means to be open-minded in science. And Avi's written a lot about that recently. And Peter has also written a lot about things like that and the nature of time. And a lot of these questions also have to do with time. For example, what happens inside of black holes. But what I wanted to do is start by going back to something Kelsey said just a minute ago, where she said that empirical inquiry was science. And there's a big debate that I'd really like to hear everyone's opinion about whether or not a theory or a theoretical idea that at the moment cannot be tested, string theory, or things like that, cannot be tested in detail, empirically, or with observations, or with experiments, is in the realm of physics or philosophy or something else, and whether we need to treat that in any way differently than theories that can be tested. And then I have another question that follows up on that has to do with creativity, but I'll just foreshadow it by saying that word and pass the mic to, oh, you have your own actually, so go ahead, everybody has a mic. I took someone else's. Okay.
Is it on? Okay. Well, first, thank you, Kelsey. I very much resonate with everything you said. I just wanted to highlight one point that one of the questions that was asked is there intelligent extraterrestrial life? And in particular, a subclass of that life could be intelligent. And if it exists, if there is a smarter kid on our cosmic block, that would be of great benefit because we can ask them the rest of the questions. Maybe they figure them out and it will save us a lot of time. So I just wanted to point this out. With respect to the question of theory and observations, I mean, I started as a theoretical physicist. I very much appreciate basic principles, but I also very much appreciate that we should be humble and learn from experiments. And it's not so much whether a particular theoretical model or idea is not testable right now. It's whether the community that works on it for 50 years can tell you what would be the guillotine that would chop off the head of this theory. And when you ask people in string theory in particular, they tell you it must be right irrespective of whether in the next century or 2 centuries we find evidence for it. So that is my problem, because traditionally, it was Richard Feynman who said 50 years ago, he said, it doesn't matter how smart you are. It doesn't matter how distinguished you are. If you have an idea that does not agree with experiment, you are wrong. And that is the sense of humility that any theoretical physicist should have. We are not in the business of showing off, of impressing our colleagues in order to get awards, honors, and prizes. We are not in the business of being a cult of people who believe in something. I mean, you can have 500, you can have 1,000 practitioners who agree that there are extra dimensions and talk about it and write papers and do intellectual gymnastics and impress each other that they are very skillful mathematicians. But that is not what physicists are about. Physics is about describing the physical reality that we all share. And if this group of 1,000 people is unable for 50 years to test their ideas, is unable for the next century or 2 tell us what experiment will prove their theory wrong, then that's not physics, okay? Because physics is the learning experience. We are supposed to figure out from nature whether we are right or wrong. We're supposed to learn. And the only way to learn, in my opinion, and I was just on a podcast a couple of hours ago, the only way by which we can learn something new is by paying attention to anomalies, things that do not line up with what we thought about before. So it's really paying attention to anomalies that the NSF and NASA should fund. But instead, what you have are committees of mainstream practitioners who built their own echo chamber and are funding people who think alike. Now, this is completely fine in the realm of religion or other belief systems. But I argue that at least 10% of the budgets should be allocated to risky projects that explore anomalies, rather than to a group of theories that say that must be true. And I rest my case.
Well, first, I want to thank you for this book, which I very much enjoyed reading. I thought it was very beautifully presented with a combination of vivid metaphors, analogies, but also connected and built on itself and added up to more than the sum of its parts, which I very much appreciated. I think that, if you think back about the history of philosophy of science, which really got going in its modern form in Vienna in the post-World War I period. And they were determined to get rid of a certain kind of speculative, authoritarian, often theologically driven philosophy, and they wanted everything to refer back to immediate sense perception, smell, ozone, here, now. And that's sort of what they call protocol sentences or protocol utterances were supposed to add up to all of science, and theory was relegated to a kind of index or organizing principle for these more basic assumptions, joined with the new logic, which so you would have these protocol statements joined by logic, for any this, there's a that, and that had been developed by Whitehead and Russell and others. And so one of the things that's happened over time is that this picture has been knocked about in 2 different ways. One of them was people realized that experiment is much more than simply recording needle pointings. And there are many kinds of experiments. There are exploratory experiments. There's finding new phenomena. There's pointing to new domains that haven't been looked at before. There are testing theories. But it's not all about just a simple picture of one kind of experiment. The other side has been an expansion of the notion of what theory is. And Einstein to take a prime example, was always very conscious of the need for a joining of epistemology, how we come to know and secure our knowledge, with the calculations and other conceptual developments of the field. And theory has many aspects. Sometimes philosophers have emphasized the predictive role of theories, and that's certainly important. And there are people, a philosopher comes to mind, Nancy Cartwright, for example, sees that as the prime virtue. Of all the virtues of theory, that's what counted, making predictions. But there are other kinds of roles for theory, including explanation. And sometimes explanation and prediction don't pull, as one might hope, all virtues in the same direction. Sometimes we have fundamental theories that are rather distant from how to predict things. If we relied on quantum electrodynamics to tell us how to fix a computer or a radio, we would never get anywhere. And so sometimes the ultimate explanatory structure and the concepts on which we base our theories require supplementation, for instance, in rules of thumb and heuristics, a term that Einstein really introduced in its modern form into physics. Sometimes you do things in theory that are not fundamentally understood. When Einstein introduced the idea of a quantum of light, and people said to him, well, how does this connect to the fundamental nature of light, and how does it add up to wave phenomena? He couldn't answer those questions. He said, for a class of phenomena, this is a way forward. And taking it seriously took another half-century before it could be brought together with the wave theory of light in quantum electrodynamics after World War II by Feynman, Schwinger, and Tominaga. So I think that theory has these different orientations and different roles. Sometimes they really hit each other hard. In the period after World War II, there was a group of theorists that thought, really, we should give up on this idea that even quantum electrodynamics was a model for how to go forward in other branches of fundamental physics. And they said, no, let's just look at input-output, black box, what was what's called among physicists S-matrix accounts. Just look at the scattering and don't ask what happens inside that box. And the other side said, no, we want to know at a much more fundamental level what this theory is. We want to open the black box. We want to say something about those interactions. And then later, even more theoretical reflections on the theory itself to ask questions like, should these theories always give finite results that could be used and connected to experiment? But that was a long way. It was called renormalization. There was much debate about it. Was this really fundamental? Was it a stricture on all theories or only approximately so? These were big debates. So I see theory and experiment as having many subcultures within each, and the task of finding a way that they can speak to one another is one of the great challenges of the contemporary period. And one of the things I like about the book that you've written, Kelsey, is that you attend with a kind of sympathetic eye to alternative theoretical accounts, for instance, of time or of the question, what happens before the Big Bang, or is there anything before the Big Bang? Questions that are philosophical as well as theoretical physical. And I think this opens up a way of thinking about science and physics in particular that has a kind of respect towards the complexity of theory, not in its mathematical articulation, but in the roles for theory, which are different and have been different at different times. Sometimes the right thing to do is just to emphasize the predictive, as in the creation of quantum mechanics. And Bohr said, let's talk about what we can talk about and go no farther. And other times, the desire to open the black box and dig deeper has had enormously important results, like the development of particle physics or taking seriously the predictions of general relativity, even in domains that Einstein thought were hopeless, like black holes or gravity waves in various ways. And sometimes it's a long pass from 1915, 16, when Einstein developed general relativity, to gravity waves, seeing a black hole in imaging and other things, and there's much more to come. Sometimes science unfolds really slowly, and that I think is something that we have to respect.
So I want to add something here, which I think is a wildly unpopular opinion, and I think likely to be met with great skepticism, which is, you're right, and I would expect it of you. So I spend a lot of time, probably more time than it is healthy, thinking about epistemology and what it means to know things. And the wildly unpopular opinion that I hold is that I tend to be to fall into a camp which is called global skepticism, which means I'm not actually convinced we know anything. And as a scientist, that is kind of like, it's a pretty vulnerable thing to admit, because we live in the world of empirical inquiry, which has been, I think, demonstrably pretty successful. But one of the fun experiments I do in my classes, well, I think it's fun, my students hate it, is when we do a unit on epistemology, on knowledge and what it means to know things. And I ask my students, and I'll ask you, to think of three things perhaps that you think you know. And then I go around and I ask them what they think they know. And it's usually, my name is Bob, or I'm wearing blue pants, or I was born on July 7th, right? Things like this. And I push them. I'm like, well, how do you know your name is Bob? Like, well, my parents told me. Okay, I'm a mother of 3, and I say with some authority that every parent in the history of humanity has lied to their children. And if I'm disillusioning you, I'm sorry, but that is just a fact, right? So if you're gonna argue to me that you can 100% trust your parents, I'm gonna push back. Maybe 99.9%, but that's different than 100%. Likewise with birth certificates, like, how do you know the day you were born? What's on my birth certificate? Really? Are you gonna tell me birth certificates are never forged? Because I'm gonna tell you they are, right? And so it comes to this, there's a whole framework called the justified true belief. And it comes down to, what do you consider sufficient justification? And mostly we have to live in a practical world, right? We have to believe that when we sit in the chair is gonna be there, or we're just not gonna function. And so I have a lot of cognitive dissonance, because clearly I go about daily life for all intents and purposes thinking things are true, but intellectually, I'm not actually convinced. And this makes my life actually really hard, and it makes life for my spouse even harder. But the reason I bring this up is that it gets to the point of empirical inquiry, right? Empirical inquiry, science, right, is really good at what it does. The point of empirical inquiry is to test things that are testable. But, and this is an argument I will go to the mat on, it can never prove things with a capital P. All it can ever do is assemble more and more and more evidence and higher degrees of confidence, but it's never 100%, right? There's always a sliver there where we could have done something wrong. We could have misunderstood something completely differently. And again, I don't want to get into a debate about practicalities, because clearly I'm a scientist and I believe in science. But I find that I have to hold that sliver open for empirical inquiry not being what we think it is. And so in this fun thought experiment I do with my kids, I hope some of you were thinking of things you think you know. And I realize we're sitting at Harvard, and so some of you were like super smart. And some of you probably thought like 1 + 1 = 2, right? I don't know how many of you like went to math. Like, math, I think, is as close as we can get to actually knowing things. But, and this is, I'm absolutely sure that you know this story, right? You've probably read Principia Mathematica. There's this famous book, Whitehead and Russell, and you just brought them up. They went about trying to prove 1 + 1 = 2. It took them over 300 pages. And even that proof required axioms or assumptions. And so this is why I just want us to always hold open a tiny little sliver of what if we're totally wrong.
On that note, Avi said he had something else he wanted to add.
Oh yeah, I just wanted to say that for all practical purposes, obviously we don't need to be perfectionists, but just to give an example. If we had a theory of quantum gravity that is unique, that unifies the two pillars of modern physics, quantum mechanics and gravity, then we would figure out probably what happened before the Big Bang. And that is just like having a recipe for a cake. If you know the ingredients, you know how to put them one after the other, and put enough heat to the system, then you end up with a cake that is quite tasty. And you need an oven, of course, but even theoretically knowing the recipe is very satisfying. Now, my point is it has a practical benefit because then we can apply for the job of God. If you can demonstrate that you're able to create a baby universe or understand how a baby universe is produced, and that's the main qualification you need for that job. Now, whether we understand it deeply or not, being able to apply for the job of God is, to me, quite satisfying. You know, it's if a sufficiently advanced scientist is able to get to the top of the food chain, there is nothing better than that. Now, there may be a deeper understanding. I don't care about it if I can design an experiment. Now, having the oven is a separate matter. We might need an accelerator, a collider that reaches the Planck scale. That may be the case. But the point is, if you know the recipe by itself, you know, that's an amazing accomplishment. I don't care much which date I was born, whether I have pants of a certain color, but if I knew how to create a baby universe, that would make me happy forever.
Okay, perfect. Thank you, Avi. So on that note, there are a few questions here that actually connect to that in a strange way. So it says, for example, what happens inside black holes? Where did the universe come from? Are there hidden dimensions? And Avi just said maybe he wants to create a baby universe. And so maybe Avi Loeb can create his own universe someday, but maybe some previous Avi Loeb created the universe that we're in. And then in that universe, there's another universe that was created by another Avi Loeb and another and another. And by the way, that is why Kelsey gave me the painting of turtles all the way down, okay? And so you wind up with this problem, and in Kelsey's book, at one point, she discusses the famous, are we living in a simulation problem, right? And how would we know, okay? And Avi's gonna answer that question in a second, but what I'm gonna do is try to make this about things like black holes and wormholes, okay, where we actually have no empirical evidence, okay, about what would be really inside of a black hole, and could you have wormholes to another universe, or what really is dark energy, but let's leave that out of it for the moment, okay? But where you have these problems in modern physics where you actually just really, really, really don't know. It's not like you think you know and you don't know. It's like you don't know, okay? Then that was my creativity question. In other words, to go past that boundary, right, you have to get inventive and you have to make stuff up, and then you have to be able to test it. And so part of what I wanted to discuss tonight is that making stuff up? Is that, informed guessing? Is that still part of science, or is that philosophy or something else?
It's an initial step, informed guessing, but I have actually a way of telling whether we live in a simulation.
I can't wait.
And in fact, I was discussing it with a person who builds the best atomic clocks in Colorado, John Ye. And the point is that atomic clocks, and the best atomic clock, based on our calculations so far, can get us to set a constraint on the frame rate of the simulation that we live in. So suppose you are living in a simulation. A simulation has snapshots, just like a movie. And if the frame rate is high enough, you wouldn't notice. You would think it's a continuous time that you are living in. And the question is, what's the best limit? The question that I asked Jan is, what's the best limit we can put on the frame rate of the reality? If we bring it all the way to the Planck scale, the minimum time scale we can imagine, then we probably don't live in a simulation, okay? Because what would happen is, if if the clock rate, ticking rate, gets close to the frame rate, you would notice that you have discrete time. The time appears with a discrete separation. Just as if you watch a movie and you would see that there is one frame after another. You can't get in between them, okay? And So we actually were able to derive a limit which is only 14 orders of magnitude above the Planck limit this morning via email. But my point is that we are planning to write a paper about it and actually explain how a future clock will be able to get us to the Planck scale. So we can tell if we live in a simulation in the sense that we will not observe in the discrete time, but
This is great. So Avi doesn't know that this is the conversation we were just having in my class, and we were trying to explain to students just how small the Planck time is, and we didn't think it was measurable. So I can't wait to.
Well, we are 14 orders of magnitude away.
Well,
I have to say,
It's not a lot. Avi says 10 to the 14 is not a lot.
Accelerator, Large Hadron Collider at CERN reaches maybe 10,000 times the rest mass energy of the proton, okay? And that is, I mean, the Planck scale is 10 to the power 19 times the rest mass of the proton. So we are talking about 15 orders of magnitude away, but it's, you know, right now the atomic clocks reach that, but we can get there without investing $10 billion. That, you know, actually
that's good because we don't have any science funding anymore.
It's okay.
I have to say,
Discussion.
I talk about exactly this in the book.
One of the things that, first I want to say something about knowing your own name. I'm one of the people who didn't know his own name. So when I was a child, I asked my mother why I was called Peter Louis Galison, and she said, well, because I like the name Robert Louis Stevenson. So I said, well, so how do you spell Louis? And she said, I like the name Robert Louis Stevenson. So I took the book, looked at it, Louis, and I said, my entire life, that's how I've spelled my name. So around the time I turned 40, I had to apply for something, I forget what it was, that you needed a birth certificate. So I wrote to New York, I got this decaying-looking black and white birth certificate, and it says Peter, Lewis, Galison. So I called up my mother and I said, Mom, how could I be misspelling my name? You said you named me after Robert Louis Stevenson. And she said, I didn't say that. I said, I like the name Robert Louis Stevenson, but your father's damn relatives made me spell it Lewis because there was some Lewis in that side of the family with a W. So my entire life, every book, every article, every document I've ever signed is spelled incorrectly.
That's brilliant.
Pretty sure that's going in Kelsey's next book.
100%.
On the topic of simulations, I mean, one of the things that's very interesting about the history of knowledge in some way, of epistemology, of how we gain knowledge, is that things that weren't part of knowledge, like statistics, have become part of it. There was, in physics, much later than astronomy, it was really around the time of quantum mechanics that people regularly quote error bars, even simple plus or minus error bars, let alone the more complicated statistics that astronomers have been using for a long time, since Gauss and beyond, that are used in the social sciences and psychology. I mean, physics is really late to the statistics party, and it's been less than 100 years that it uses it in experimental science in a very systematic way. Another example is simulations. Simulations has come to be a kind of third term that mediates between experiment and theory. We can't do a lot of experiments in particle physics and astrophysics and many other domains without being able to simulate things that we can't just read off from equations like the long-form version of the standard model that you reproduce, the Lagrangian in your book. And so we can't do that. And so in the absence of either direct experimental knowledge or direct theoretical knowledge deduced from first principles, we have simulations, and we use them all the time. And there was a period when people would say, oh, well, a simulation, that's just a stepping stone. Now go back and figure out what's really going on with an analytic, a short form theoretical deduction. And people say, why are there islands in comet tails? And you simulate it and you show that they're there. And they say, okay, that's nice, but what's the term in the equation that shows me where the island in the comet tail is. But at a certain point, generations changed, and people say, if you can say, using the fundamental laws of gravity and other things that we know in mechanics, you can deduce the shape of galaxies or something else, you have understood it. And so I think that science and laws, our understanding of physical laws, will continue to evolve. I don't think there's any reason to think that quantum mechanics in its current form or general relativity in its current form in 200 years are going to be the standards of how we think about fundamental physics. Where they'll be, I'm not sure, but it seems likely that they'll be as far from what we think of now as fundamental concepts as Einstein is from Newton.
Yeah. I would love to come back to the role of creativity in this. Mm-hmm. And Alyssa, your question, which I think is really unsettlingly probing, like what is creativity and what is its role in science? And I'm going to share with you a perception that I hope is not a reality everywhere, but my perception is that we almost train creativity out of people, in the sense that we have, experiments that like millions of people have done and there are right answers. And if you think something that's a little bit tangential to prevailing wisdom, you're crazy. And I feel like those are paths to dead ends and cutting off lines of thought and inquiry before we've let them run their course. So for example, I happen to think, we're not going to talk much about, I think, like dark matter, because that would be a whole lecture. We don't know what dark matter is. That's the spoiler alert. But there was a theory on the table to explain dark matter that was called modified Newtonian dynamics, or MOND. And a little bit crazy, right? It requires throwing out not totally throwing out our understanding of gravity, tweaking our understanding of gravity, which is one of those things that we think we understand really well. I happen to think that MOND is wrong, but I happen to think it was really good science, in the sense that they asked these questions, this what if? Like, what if our understanding of gravity is wrong? Can we give ourselves permission to follow that thought experiment? And maybe we find out, okay, well, that thought experiment didn't produce any fruit, and that's fine. But let's not cut off that line of thinking before we give ourselves permission to ask some maybe what sound like crazy questions.
This is perfect. And you said ask questions. And so it is now the time in the evening. You realize that Peter and Avi and Kelsey and I could just sit here and talk all night about this. And I'm tempted to start looking at these other things. But I hope you get the idea. You see already, you ask one question and you connect to the other one. And all of these are interrelated. And what I cannot recommend highly enough about the book, and Peter kind of got to it, is the book builds on itself. And so first we'll talk about extraterrestrial life, and then and we'll get bigger and bigger and bigger, and somehow you're understanding string theory. And so I recommend the book. I'm not paid to do this. I just really recommend it. And now
I did bring you chocolate. Does that count?
What'd you say? You owe me what?
No, I brought you chocolate, so I did bribe you.
She did.
But it turns out she doesn't like chocolate, so it wasn't a very good bribe.
Meryl, is it true that I don't like chocolate? Much? Yeah, see? There you go. Anyway, so we have these microphones that I can throw at people, and that sounds really fun. So if you'd like to ask a general question or a question of a specific person, you are welcome to. Oh, and of course the person who's asking the question is way in the back.
I'm wanting to see your football arm.
You want to see if I can throw it?
I do.
Okay, I cannot throw this microphone that far, but I will try.
I hope this is on video.
Whoever catches it, could you please give it to the woman in the orange shirt behind you? Oh, all right. It's on an empty chair. And then Eric also has a
Who is it going to?
That I got.
This is really easy. I'm just looking straight ahead. Ari, what is the nature of time?
Oh, that's easy.
You're asking me?
I am.
Obviously, I think she's asking you, Avi.
Well, it's really a very fundamental question, because time is quite different than space. And if you look at quantum mechanics, the equations separate time from the rest. So I guess the way I think of it is that things are not the same. The reality changes, and time basically is a tag that you put at each instant on the changing reality. So nothing stays forever. You know, we tend to think that the Earth will stay habitable forever because it could be much longer than our lifespan. But the truth is the sun within 7.6 billion years will become a red giant and will engulf the Earth. Even before that, 1 billion years from now, it will boil off all the oceans on Earth. But eventually, it will engulf the Earth will sink to the center of the sun. The sun will disappear as a star. Afterwards, it will become a white dwarf. The core will contract to a size similar to the Earth, and it will become a metallic sphere the size of the Earth, and the Earth will be embedded in it. You know, things change, and we are just transient actors on the cosmic stage. Completely insignificant, by the way, and we tend to think that we are the pinnacle of creation, that there is nothing like us. But the truth is that nobody cares about us. Okay? And
How is this the nature of time?
well, because things change, and the universe will be very different in billions of years from now. And so time is just telling you where we are in this series of events that started in the Big Bang. So there was an initial time when the universe started from a very hot and dense phase, and the future is unclear, but especially if dark energy is evolving the way that we heard last week from a new paper. But altogether, I think time is just a tag that tells you where we are now. The universe is really special because it was nearly uniform at any given time across large scales. And that makes, if you put clocks in the universe, and you initiate them at the Big Bang, they will all tick at almost the same rate. And therefore, there is a sense that you're slicing the history of the universe. If you use time, you can get a very nice ordering of what happened in the universe. It started from a simple initial state and became very complex. So time is special in that sense because the cosmos gives us this ability to slice its history from the beginning all the way until now with clocks that tick at the same rate everywhere. The variations are really small, 1 part in 100,000.
Kelsey, do you want to say anything about the game we played with the students and that you play with your students about this question?
I'm like, how much time do we have?
Oh, a minute.
The irony.
Time for time.
Time for time. You know what, time is really interesting because I would argue that time is the thing that we simultaneously have the most exposure to and the least understanding of. And I think it's a very slippery concept. And Avi is, dipping into what has been a very long-standing philosophical debate about the nature of time and whether it exists in and of itself or whether it's simply relative, markers of relative things that happen. And lots of great thinkers have been thinking about this for a very long time. I think the jury, to some extent, is out.
Peter knows a lot about
Yeah, and I should just really hand this to Peter is what I should do. But I do think about the nature of time a lot, and I think I have some alternate perspectives than Avi's on this. I don't think that it is just a marker of how things happen. I think it is an actual thing. And anyway, I have lots of thoughts on this, but I'm going to stop talking.
No, I think that's a read the book moment. But Peter, because you've studied time.
I mean, one of the things that Newton did was to say there's an absolute space behind the space that we measure with rulers only approximately and imprecisely. There's an absolute time that's clicking like the flow of a river behind any clocks that we might imagine to have. And Einstein, said, actually, that's not a good way of thinking about it, that the measures that we have are connected to what time and space mean. And moreover, time and space are tangled up with one another, that what from one perspective looks like a difference in space can look in like a difference in time in another frame of reference. And that continues and gets more, further articulated in general relativity. And in black holes, there are really strange things that happen. When you cross the horizon, as you could in a large black hole without too much upset, aside from not being able to leave again, you could fall through. But inside a black hole, time and space begin to switch their roles. In our world, time is always going in one direction, but we can walk to the back of the room and return. We can't do that with time. Inside a black hole, once you cross the boundary, you're going in, and there's no even standing still. You can't fire your retro rockets and stay just inside the horizon. You're going in. It would take an infinite amount of energy just to stay still. So, and space begins to take up, time begins to have aspects of space. And then if you cross even a spinning black hole inside what's called an inner horizon, then it even seems as if you might be able to circle around or and come back to an earlier point in your own existence. So things are very disturbing, and it's these sorts of things that make philosophers very interested in black holes, as are mathematicians, as are astronomers, because these questions of causality are disturbed by the way what happens in black holes.
So I think you're definitely getting a sense of how these questions are related. I think Eric was next.
Yeah, so I was thinking about while Avi was on his diatribe about string theory, lack of falsifiability. So it seemed to me that Newton's
Can you put the,
Newton's theory of relativity, special relativity, right, was almost built on pure thought, right? Because if you take the constant speed of light, and then you require that the laws of physics are the same in all frames, and the constancy of the space-time interval, which I think you could get derived from the fact that the laws of physics are the same. Well, I haven't done it myself, but was there an empirical basis for special relativity? Or, there must have been some, but
Michelson-Morley experiment, there was definitely a need to explain some facts that were not understood at the time without
that's
special
what I'm
relativity.
asking. So what was the empirical basis for the special relativity?
Experimentally, it was, I mean, people have had the theory of ether that implied that perhaps the speed of light will change in different reference frames. And experimentally, it was found to the precision back then that the speed of light is the same in all frames of reference. And Einstein used it as a fundamental principle of his theory, not explaining it, but basically arguing that it's a fundamental principle of nature. And obviously, his special theory of relativity was tested so many times that it was definitely a very wise move to ascertain that the speed of light is a constant. And you cannot exceed it. By the way, now that you think about gravity, and we know that gravity is attractive when you have the mass of the Earth, it attracts. But if there was a sense of a negative mass, which is something you can think about in analogy with electromagnetism, you have positive charges and negative charges. And so a negative mass would actually produce repulsive gravity. And if we had access to that, you know, in principle, we can build a time machine and go back in time. In principle, we can exceed the speed of light. These things do not exist as far as we know, but so Einstein's assumption was really a good one, and combined with his formulation of space and time as being curved as the nature of gravity. I mean, we have a very good theory that stands up. Now, you may say, maybe it's not really the right theory because we need, in the standard cosmological model, we need two constituents that dominate the mass budget. One is dark matter. We don't know what it is. It could have been modified gravity. Now there is this dark energy, which until last week, it was thought that it's a cosmological constant. The Nobel Prize was awarded for two members of the astronomy department at Harvard. And the point is that if it's a cosmological constant, it's a constant of nature. Just like the electron mass, the electron charge, the vacuum has some mass density that is constant. It's a state of the vacuum. And string theory, once again, said, oh, this vacuum mass density is 122 orders of magnitude smaller than we expected, which is the Planck scale, but we can explain it because otherwise a galaxy like the Milky Way would never exist, giving rise to observers like us. So it's a small, the vacuum could have 10 to the power 500 possible vacua states, but the one that is ours allows us to exist. That was now, if it's not a constant, the way that the DESI experiment is arguing now at a 4.2 sigma level, so that's a probability of a statistical fluke at 1 part in 50,000, okay? If this holds in the future with better data, that makes it maybe 5 sigma, then it means that not only the vacuum has some mass density, which is creating the accelerated expansion of the universe, but that dark energy actually evolves with time on a timescale comparable to the age of the universe. It makes it very unreasonable, theoretically. It's not a cosmological constant. And then you ask, okay, well, maybe it means that gravity is not well understood on a cosmic scale. So it's possible that both dark matter and dark energy indicate that we are missing something.
I think we are.
Let me just clarify the question. I was saying if you take the constancy of the speed of light, right? So there was an empirical basis for that. But then, is there another? Is there some other empirical basis for what Einstein did? Because if you have the speed of light and the space-time interval, you can derive everything in special relativity just by thinking about it. So maybe Peter knows as a historian.
Yeah, I mean, there were lots of things that Einstein paid attention to in the empirical domain, including the Michelson experiments, but it was actually the simpler version of Michelson's experiment, not the very precise one that it comes to be taught in every physics class. And Einstein also had theoretical motivations that were not just empirical. He wanted a theory that, in some sense, looked like the greatest theory of the time, thermodynamics, which had 2 founding principles. Energy is conserved and disorder increases. And he had 2 principles, that the laws of physics should look the same in every frame of reference and the speed of light is constant. And he wanted a theory that extended and deepened what Galileo had recognized, which is if you're in a closed cabin traversing the Mediterranean, there's no experiment with mechanics or dripping water or swimming fish in a bowl that would tell you you were in motion. And he thought, how strange that mechanics should have that feature, but not electricity and magnetism. So he was offended by this asymmetry in the fundamental nature of science, that you had no way of distinguishing constant motion from mechanics, but you did for electricity and magnetism. So Einstein's motivations had some, he paid attention to experiment. The paper ends with some predictions about how electrons should move that were distinctive to special relativity. But it wasn't just empirical. It was also a kind of a philosophical commitment to what a theory should look like. It was, in fact, a kind of meta theory. It was a theory of how theories should look.
There's also a lot of that in Kelsey's book, and there's a lot of discussion of symmetry, and physicists and scientists in general love of symmetry, and that also borders on the philosophy and aesthetics. I think we have time for one more question, and we have like 20 more questions, so let's see what we should do. There's a very small person who's trying to ask a question, so let's go with that. All right, can I do this? Jeff, it's gonna go right over your head. No, I can't. Okay. There's nowhere to grip that. Okay, thank you.
Is there extraterrestrial life?
Oh, that's a whole other subject. Is there extraterrestrial life is one of these questions. And I think most of us here would say yes, okay? But we would have a lot of different reasons for giving you that answer. And Avi's written an entire book, 2 books actually, about that. So can you give like a 2-minute answer?
Half a minute answer.
Half a minute answer.
Yeah, so there are hundreds of billions of stars in the Milky Way galaxy alone. Many of them looking just like the sun. And we know from the stars that we looked at closely, we know that at least a few % have a planet the size of the Earth, roughly at the same separation. Meaning that the temperature of those planets allows for liquid water to exist on their surface if they have an atmosphere. And then it's a question of how arrogant we want to be as to whether we say, if you roll the dice, billions of times, you would never get anything like us. And Enrico Fermi asked, where is everybody? And that is a question that every lonely person asks. And what you tell that lonely person is, you are not that attractive. They will not come to you. Don't be presumptuous. What you need to do is go to dating sites, look out the window, and then you will find them. And Enrico Fermi didn't really search. Now, the astronomy community wants to search, but for microbes, not for things like us, because they say it's an extraordinary claim to imagine something as good as us. And I say, just read the news. We are not the pinnacle of creation. There is a lot of room for improvement. And we should allow ourselves to look through telescopes and search for them, invest billions of dollars, not only in the search for microbes, but in the search for intelligent life.
Let's hope we can do that and a lot of other science things. So I'm just going to ask Kelsey to take the last word, and then I think we'll be able to stand around a little while, and I'm supposed to remind you that Kelsey will also be signing books. So if you purchased a book or you brought your copy or you want to get a copy, the people from the Harvard bookstore are outside. Was there anything else logistical I was supposed to say before I? No? Okay, great. So then let me give Kelsey the last word here, and thank everybody one more time afterwards.
Yeah.
Thanks.
So how I thought I might close this out is sharing an excerpt from the end of the book. And so there's a lot of stuff sandwiched in the middle, but in some ways the bookends, to my mind, are what motivated and underscore its importance. So I'm just going to share a short paragraph from near the end. My sense is that our collective willingness to embrace existential questions of reality is becoming increasingly thin amid modern life as we spend less time in nature. I worry that this growing detachment from the reality of the universe and our place in it is slowly making us collectively myopic. Over the generations, we have increasingly moved inside at night, where we have a level of comfort and safety that can make us indifferent and incurious about the outside world. The night sky has all but disappeared for over 80% of the global population, living under severe light pollution. I can't help but wonder how this impacts our worldview and sense of self and place in the universe. I conjecture that this disconnection from the universe translates into an overinflation of superficial concerns. I could well be romanticizing the distant past, but I yearn for a time when people would look up at the night sky and simply wonder.
Again, thank you very much to all of you for coming, and thank you, Kelsey and Peter and Avi, and we'll stick around a little bit, and Kelsey's got to go sign books in the back. Thanks again. Bye-bye.